Okay, what's up? All right, let's get this going. So let's make sure it's all coming together here. All right, got that. Got the tablet, and I think we're ready. Cool. Okay, so today we are going to finish off section 2.3. This is a closer look at Cauchy's theorem, and we will set ourselves up nicely to go into 2.4 next week, the last section we'll cover before the exam, and talk about Cauchy's very famous integral theorem. Cauchy's integral theorem is a heavy hitter. It is going to show us some very exciting things about analytic functions, holomorphic functions, complex differentiable functions. We're going to learn a bunch about what is really going on. And to get there, we're going to have to finish up our discussion of Cauchy's theorem, the slightly more in-depth discussion about it that we've been going through the last few days. We started out with, well, we did a lot of different lectures last time, yeah. We started out with a quick review of this path independence theorem, which I think I have said enough times that it's probably drilled into your heads. Then we went in and we proved Cauchy's theorem for a rectangle, something that will be good to remember tonight for our lecture today. This was a beefy little proof. It wasn't terribly tricky in terms of any of the manipulations. We didn't do any like brutal integration by parts or something, no tricky partial fractions or, weird arguments like that. But it had kind of a lot of steps to it. And those steps were not super immediately obvious in terms of what you should do. Gorsuch's method of repeated bisection to prove Cauchy's theorem on a rectangle is not necessarily an intuitively obvious argument. All the same, it is a very cool argument. And what it got us is that when f is a function that's defined in analytic on an open set containing a rectangle and its interior, then the contour integral around that rectangle of the function f is 0. So that led us into Cauchy's theorem for a disk. When we started talking about Cauchy's theorem for a disk, we sketched kind of the proof and what it looks like. We're going to show that the function has an antiderivative, and then via the path independence theorem, we will get the zero integral around closed curves that we want. And the trick here was to define paths nicely, look at paths to two different points like we were doing over in here, and build little squares so we can use Cauchy's theorem for a rectangle. Okay, so that was the trick right there, remember? And I have not gotten any of these yet, so I hope people take advantage of it. Do it as you're studying for an exam. It will help you understand what you're doing, and you'll get extra credit out of it. If you prove this, the proof is in your textbook. You can literally just write it down if you want to. I encourage you to understand it, but you can straight up just copy it if you felt like it. I would maybe be disappointed if you still did, if you didn't get any of it, but I don't know. That's up to you. I don't know what you understand or don't, except in terms of what I see on exams and in homeworks. So, get extra credit, try it out. Especially since it's in the book. Great exam prep. And then after that, we went into a few slight weakenings of Cauchy's theorem. We won't just continue to weaken Cauchy's theorem for the rest of class or anything like that, but we were able to handle a few different places where f might not be analytic at certain points. That is, if you had a point inside, your rectangle, where f is maybe not analytic, but at least satisfies the limit as you approach that point of z minus that point times your function is 0. That is, if the function is relatively, if it's not too poorly behaved near the point where it's not analytic, then you can handle it as long as the analytic point lies inside the rectangle. We were also able to handle the case where it wasn't necessarily analytic at a point on the rectangle itself, provided the function was at least continuous at that point. And that's actually not too strange if you just think about the path independence lemma, or independence theorem, not lemma, the path independence theorem, which only requires continuity. So remember, yeah, the path independence theorem only requires continuity. Analyticity is the key that allows us to unlock all of the statements the path independence theorem gives us as being equivalent. So what we're going to go into today and do a little bit more of is talking about some of the other things that we got out of Cauchy's theorem, other ways of approaching Cauchy's theorem, and based off of some emails I've gotten, I believe that this may touch on something that a few people found slightly tricky on the last homework, which is homotopies and building curves between points and all of that. So let's start with a little bit more formal of a definition of homotopy than what we were doing previously, and we'll build out from there. So grab a nice highlighter color and give ourselves a little bit less opacity. All right, so homotopy, definition 2.3.6. We're going to start with, and I'll zoom in a little bit closer here so this is a bit more readable. Okay, we'll start with some gamma naught, a function from the unit interval into G, some subset of the complex plane here, or really it could be any topological space. We'll have two different curves. I mean, it could be any topological space in the sense that we can define homotopy outside of the complex plane. But here it's going to be the complex plane. So we have two different curves, functions from the unit interval into a set G. These are two continuous curves from Z0 to Z1 in a set G. We'll say that gamma naught is homotopic with fixed endpoints to gamma 1 in G if there is a continuous function. And this is a great place where you can see why our definition of continuity in terms of the preimage of an open set is open is good, because the function here is not just a function from like R to R or from C to C or something like that. Although really you could regard it as a function from C to C if you wanted. The continuous function here, capital H, goes from the product of the unit intervals into G. So that's the unit square, you know, taking the product, that means just one thing that's in there, and then comma another thing that's in there, right? This is a function that takes 0, 1 cross 0, 1 into G and satisfies the following. When you put 0 in for the first argument, you get out gamma naught, right? Whatever you put in for T, you get the same thing as gamma naught. So when you put in 0, you get out gamma 0 at the point in the second argument. Okay, when you put in 1, you get out gamma 1 at whatever point you put in the second argument. All right. No matter what point you put in the first argument, at 0, you get the first point on your path. And no matter what point you put in the first argument, at 1, you get the second point on your path. So kind of visually, here's what's going on. You've got yourself a nice, the unit square here, so just, 0 to 1, right? This is like 0, 1. That's this chunk right here. And then you've got another copy of 0, 1. That's down here, right? That's a 0, 1. And so points out here have one piece in one of them, and then the other piece in the other ones. This is like S, and then T. And let me put that in like a nice... These are like our points ST. You see what I'm saying? This is in the unit square, right? So that's like this point right here or something, right? Go over and go up, right? There you go, ST. Okay, so these guys get mapped over by H into, well, what we're looking at here, you can think of it as like these lines, right? These like lines are getting mapped over to here, right? Okay, so this is maybe like the T parameter, right? And this is like the S parameter. So if I grab some, or I wrote this backwards. I guess I should have done it the other way. Yeah, I should have done it the other way. I should have written it as TS or something. Yeah, this would be the S piece. I'll just erase that to make our lives a little bit easier. Just to make it super clear so I don't cause any unneeded confusion right there. So this would be the T parameter over here, and this is the S parameter, just because we've got these lines. And I want to say that, yeah. So for a fixed S, like one of these lines, it gets mapped on over to one of these lines, right? So like this pink line right here, right? This pink line right at 0, S is 0, gets mapped onto this thing. That is, as T varies across the entire business right here, with the S parameter fixed at 0, this line goes to that one, right? And you could do the same with the next line, right? You see what I'm saying? So this line here, which is something like S is a third, gets mapped on over to this guy, and you can start to see what I'm saying, right? It just goes 1 and 1 and 1, next and next and next, right? And so these, you could do it for lines that we haven't drawn, right? Like what about like right here or something? And really this is just like a fancy, nice way of showing that, like, as one piece varies or something, these things could be, you could be moving across them at different speeds or something. So you could have a homotopy that doesn't even, you have the same exact curve every single time, just the speed you're traversing it changes as you vary the S parameter. And this is how you move across. So you can see it like the curve gamma naught turning into the curve gamma 1 as we vary the S parameter. I have a nice kind of illustration of this. Let me grab this. Okay, yeah, I just went on into Desmos and I set it up so we'd have some nice, pretty looking little points. Sorry if you can hear my son having a little breakdown upstairs. Poor little guy is tired out. Anyways, so I just grabbed like a line segment, and I, we got like one point, another point. These are like our, Z1 to Z2 or something. So X1, Y1 to X2, Y2. And I built a few different curves taking us from one to the other. So here's a straight line. This guy just goes across like this, right? And it looks confusing in Desmos because I've had to graph it out point by point, right? And just take it from take it across. 1 second. All right, sorry. Anyway, so this is just a straight line. This is the straight line homotopy between like x1 and x2, right? Just between these two constant curves. It's you just go across 1 minus t in the first argument, and then t for the second point, right? So at t is 0, you get x1, and at t is 1, you get x2, right? And it just does a nice little combination between the two. Then I built another one that is much more complicated. This is 1 minus t to the 9th, that whole thing to the 3rd times x1 plus t to the 6th times x2. Then 1 minus t to the 3rd to the 7th times y1 plus t to the 4th y2. All right. And so this is, did I just mess that up? Okay, there we go. I just accidentally pressed something I shouldn't have. And so this gives you this weird purple curve right here. So what I have here is a homotopy between the two. Now, I've set this up with a nice little slider. So at 0, it's going to give us that crazy curvy one. And then as you move it over, it'll give you the other one. So this is what's going on. As you vary the S parameter, graphing all those t points, right? Like these images of these curves. As I vary the S parameter, it moves from one to the other. And so if I drag this over, I'm going to zoom out a little tiny bit. If I go put this point way over here, because these things will change based on what the x's and the y's are, the curves look quite different. But you get these nice like little just bend one into the other, right? All right, fair enough. And that's one way you can do this. We could also, if we want to see a slightly different picture, let's just take this nice straight line, right? And let's grab a point on there, and we'll build this out. Gotta get my keyboard over here. We'll build this out again really quick with a nice similar. So I'll go 1 minus s x1 plus s x2. So that'd be my x coordinate, and then I'll do the y coordinate. So 1 minus x y1 y1 plus s y2. Bada boom. And there we go. And this will just give me a point that's like on here, so we can see it kind of move across, right? So if this is just going across like this, all right, all good, all great, easy. Notice you can watch it basically like traveling across this curve, right? Like I've built this curve, and as you vary the t parameter on this curve, this is how you'd move across it. Yeah? Now notice the same exact curve, if I say make this like s squared instead of s, notice I don't get a different curve, right? This point, even though it's like the t one, I've changed the t's into s's, and I've squared the s's. I'm still going along exactly the same path, but this is a different curve. So what I'm trying to point out here is that homotopy doesn't have to be the complicated looking picture between different curves like this. It instead can be as simple of a picture as two identical curves, but they're just going at you're going along them at different speeds. Those two curves are also homotopic. And so that is an important thing to note. And hopefully this kind of gives a better picture of what things look like. It's just ways of bending one shape into another. So we can bend paths into other paths and get a lot of cool little pictures. Just moving from one to the other and so on. Right? Kind of cool. Kind of nice, satisfying animations, yeah? Anyways, let me jump back over here and move my keyboard. Okay. So, okay. Now, we're going to also need a version of this that makes sense for closed curves. So homotopic with fixed endpoints just means that we're not moving the endpoints of the curve, we're just deforming one curve to another. Now, the kind of obvious thing that you could have is you could have homotopies with fixed endpoints. That is, z1 and z2 could be the same, right? But there is a subtle difference. Namely, if you want to think about, you could have like this curve starting from here and ending here, and then you could have a different curve, right? Starting here and ending here. One way under the other definition of homotopy, or like what we've talked about before with homotopy with fixed endpoints, one thing I could do is that partway through, I could have it, well, if you're not using homotopy with fixed endpoints, you could have the curve disconnect in between the two, right? You could think of it like if these are like like a knot tied together. You could untie the knot briefly and then like move it around and then retie it, and then you've deformed it from one to the other. And so this is the thing we have to make extra care of to make sure we avoid when we're talking about homotopies with closed curves. So a function, two functions from the unit interval into G, gamma 1 naught and gamma 1 are, if they're continuous closed curves in a set G, we'll say that they are homotopic as closed curves in G if there's a continuous function. Continuity is important here. H from the unit square into G, such that when you plug in 0 into the first argument, then you get out gamma naught. Nope. When you plug in something to the second argument, right? When you put in 1 in the first argument, you get out gamma 1. And no matter what you plug into the first argument, at 0 and at 1, you get the same thing. So as you vary that first argument, you maintain that fixed base point for your closed curve. The place you start and stop doesn't change, right? Okay, so you can move from here down to here, right? And you're never disconnecting the curve. Does that make sense? So maybe I don't want to use a highlighter right there. All right. So once again, it's the exact same picture we were doing before with grabbing like a line here, right, at S is 0, and getting out this curve from H, right? And unfortunately, these curves are a little bit harder for me to trace around. Sorry for the mess up over here. And then, so on and so forth. The next line gets mapped a little bit into this next one right here, and so on and so on. Does that make sense? I hope so. So this is just extending the concept of homotopy, or not even necessarily extending it, but adding this suitable restriction to ensure that we maintain a closed curve throughout the entire homotopy. All right, so these notions of homotopy, one, let us get a slightly better version of a simply connected set from before. So remember when we were talking about simply connected sets, where that was where we had the picture was that like here's a set, and let me draw another set. And I'm going to highlight these guys a little bit. So here's one set. Here's a different set. All right, there we go. Okay, so one of these guys is simply connected, and the other one is not simply connected. Both of them are connected because they're path connected, right? If I pick two different points, no matter where they are, I can always find a path between the two. However, I have holes in one of them, right? That is, if I have one path and then I have a different path, I can't continuously deform one path into the other path without going through a hole, which means leaving that set, right? Leaving this set. So it's not simply connected. However, over here, if I have one path, no matter where it goes, I can always deform it into any other path, right? So simply connected is all about whether or not every path can be deformed into another path via a homotopy with fixed endpoints. Now, one other way to see this, just, kind of connecting these guys, is all about whether or not you can, looking at this picture up here, sort of with the curve shrinking down, all about whether or not you can shrink down a closed curve into the simplest closed curve. That is, a closed curve, a point is certainly a closed curve, right? So, gamma of t equals some point z naught. This is certainly a closed curve because gamma of 0 equals gamma of 1 equals z naught. It doesn't change. It doesn't go anywhere. It's certainly continuous. It's constant. So one thing that's nice is that if you have I should not draw that dash because I'm not drawing like a set here. I'm drawing like a curve. If you have like a curve that you can kind of shrink on down, right? Then you have a curve that is homotopic to a point. You see what I'm saying? You can, if like a certain curves can be shrunk down small enough, then you can get them all the way down to a point. And so like gamma of t, I should have drawn this in like a different color or avoided reusing that same color again. This guy, if you just shrink it on down, then you get a point, something like that. So if you have like, say like this curve, like let's call this like gamma 1, and we'll call this other guy like gamma naught. Gamma 1 would be homotopic to a point if you could shrink it down to that point right there. Now, the difficulty to shrinking something down, if we're looking at this all in like some domain and we want it to be homotopic in this set G here, right, might come if I have, say, like a little hole in G right here, right? So if I'm looking at everything in G, and I have everything except that little hole, then I can't shrink gamma 1 down into that point or any point because I always end up getting stuck on this hole right here. No matter what I shrink gamma into, I can't shrink it down past that hole because the hole's right there. So being contractible, as some people like to say, or homotopic to a point is a nice property because it lets you detect simply connectedness in the sense that, and this is a great alternate definition for simply connected, a connected set G is simply connected if every closed curve gamma in G is homotopic, as a closed curve, of course, to a point in G, that is, to some constant curve. So simply connected just means homotopic to a point. That is a nice and easy way to check it. Just think, is there a loop that I can't shrink down to nothing? If it seems weird that you could take a loop and push it down to a single point without losing anything, just in case this is helpful, here's kind of an example if you want to think about a curve. So you have like gamma of t, and I'll write it in coordinates or something like that. It would be like cosine t, or even if I want to make it from the units interval, 2 pi t, or actually here, I don't even need to write it like this. Let me write it like it's all in C, since this is a complex analysis class. Cosine of 2 pi t plus I sine of 2 pi t. This will just trace out the unit circle, right? It'll just give us a circle, yeah? Well, let's show really quick that you could build a homotopy. Let's call this H of ST, and just define it to be, let's call it S gamma of t, right? And this will be a homotopy between gamma and the other path right here. I don't know. Let's call this. Let's even call this gamma naught, gamma 0, and this will be gamma 1 of t. Let's just make that equal to 0 in the complex plane. So the constant path. This is a homotopy between the two, or even I'll make this, how about I'll make this 1 minus s. It's still a homotopy either way, but just to make this a little bit nicer to see as we vary everything, I can actually even do this in Desmos. Gamma naught of t. So this is just going to be, when s is 0, we get out gamma naught, that's the unit circle, and then as we increase s towards 1, we just get progressively smaller and smaller circles, right? So we get like a circle like right in there, and then we get like a little bit smaller of a circle and like a little bit smaller, and when we get all the way over to 1, then that's 0, right? And so hey, we've gotten gamma 1, right? So that's what a homotopy to a point would look like, in case that makes you feel weird at all. Okay, we can also get some other stuff out of this. We can get a notion called convexity. This is a relatively obvious notion. So if a set A, a set A is called convex if it contains the straight line segment between every pair of its points. So contains straight line every pair of points. That is, if you've got z0 and z1 in A, two arbitrary points, then so is s times z1 plus 1 minus s z0 for every number s between 0 and 1. So the way to kind of visualize this, going back to our simply connected, or even I'll draw a slightly different picture right here. There we go. So here is a set that is, set that's convex. Pick any 2 points inside of it. Here's one. Straight line between them is in the set, right? Here's a set that wouldn't be convex. I'll just erase a little bit of that guy and put back in. Oh, come on. This is connected. This is simply connected. But notice that if I grab a point here and a point here, the straight line segment between them is outside of the set. So not convex, right? So convexity just says, hey, can you go between any 2 points without leaving the set in a straight line? You can go there in a different way, a non-straight line. So it's connected, it's path connected, but you can't go there in terms of a straight line. So that's convexity. All right. Here's a proposition. If A is a convex region, if A is a convex region, then any 2 closed curves in A are homotopic, and any 2 closed curves with the same endpoints are homotopic with fixed endpoints. This is exactly like the kind of picture I was showing with that Desmos animation. What did I do to get between those two of them? If we jump back to it, here, how I actually ended up building out this nightmarish function right there that took us between the two was I took the x-coordinate from my straight line, right? And then I multiplied it by s, and then I took 1 plus s times the x-coordinate from my weird curvy line, right? And then I did the exact same business with the other piece, the y piece. So I just did a straight line homotopy between these two things, and that means that I just translated every point across in a straight line, and that's all the business that happened right there. So I just took, and this is how you'll prove it, you just take 2 different curves, gamma naught and gamma 1, okay, and then we'll define h of st, this homotopy, by s times gamma 1 plus 1 minus s times gamma naught. That way when you plug in 0, you get gamma naught. When you plug in 1, you get gamma 1, since 1 minus 1 is 0, right? Okay, and this is just the easiest straight line homotopy you can make between 2 things. All right, cool. And it's in, and because we have convexity, this is why we're allowed to do it and stay inside of the set, is because every pair of points on these 2 curves lies in the line segment between them, stays in the set. So if I deform one into the other, just, plug in a value for t, then as I vary s, I'm guaranteed to stay in the set. And that's the whole business. So the straight line segment between them is in the set A. It is a continuous function, since each of those guys are continuous. And at s is 0, you get gamma naught, and s is 1, you get gamma 1. That's exactly what I just said. And if they're closed curves, then you get exactly what you want. So h of s0 is equal to h of s1, just because of the straight up do the calculation. Put in 0, s times gamma naught of 0 plus 1 minus s gamma naught, or gamma 1 of 0, gamma naught of 0, because we can switch gamma 1 of 0 with gamma 1 of 1 because they're closed curves, then we just do that. Same thing with gamma naught. And then, hey, look, that's h of S1, right? So closed curve homotopy between the two. And if they both go from Z0 to Z1, then you get the analogous conditions by doing exactly the same trick in each for 0 and 1 right there. And it's a fixed endpoint homotopy if that is the case. So it's a very routine type of proof. You just go through and you verify that all of the conditions relative to being a closed curve homotopy or a straight line homotopy are indeed satisfied. So this is a lot of topological discussion. And what this will do is it'll give us the deformation theorem. But we should just mention, at least briefly, and this is such a simple proof that it's kind of nice just to have it in here. Corollary 2.3.11, a convex region is simply connected. This is kind of obvious. After all, if you can go between any 2 points with a straight line, then you have a path between any 2 points, right? So convex regions are obviously going to be, well, they're obviously going to be path connected. And so since path connected, subsets are simply connected, that's proposition 2.3.10, I believe, or no, that's an earlier one. They're doing a slightly different proof right here. But since path connected regions are simply connected, we're obviously going to get that a convex region is simply connected. This little proof right here starts by just going, hey, let's take any point, then any closed curve is the constant closed curve is certainly closed, and the two are homotopic by this nice proposition we had right up here. And so if every closed curve is homotopic to a point, then it's definitely simply connected. But you can also get it the other way I just mentioned. So anyways, why have we been doing all of this? What is the dang point? Would you guess? It's the deformation theorem. That is, if we're talking about Cauchy's theorem, we've got it for a rectangle, we've got it for a disk, let's get it for any dang closed curve. Let's go for the deformation theorem. This says that if you have a function f that is analytic, f is an analytic function on an open set G, and gamma naught and gamma 1 are piecewise C1 curves in G, then if gamma naught and gamma 1 are paths from Z0 to Z1 and are homotopic in G with fixed endpoints, then the contour integrals about them are the same. Similarly, the exact same thing for gamma naught and gamma 1, if they're closed curves, which are homotopic as closed curves in G, then you get exactly the same business. You get that the contour integrals about them are the same. All right, this just means that you can deform curves, piecewise C1 curves homotopically into each other and get everything you need. So I won't prove this in its full scope, run through every piece of it, because it does have some, it's kind of a long one, just like the proof of Cauchy's theorem for a rectangle, and it's much more instructive just to give you a sketch of what the proof looks like. So the whole idea is to take our homotopy, and we'll talk about the homotopic with fixed endpoints, the case where we don't have closed curves, right? We're looking at just paths from point 1 to point 2, right? We take our homotopy and we build like a little grid, right? Pick some points on the s-axis between 0 and 1, pick some points on the t-axis between 0 and 1, and then we're going to look at this grid and we're going to map it on over into G. And we're going to get, from the t piece right here, when s is 0, that'll map on over to this piece right here, right, and so on and so forth, right? We've drawn this picture before. We got this fixed endpoint homotopy. Okay, fair enough. And what are we going to do with this? Well, the idea is to grab little rectangles and we'll map it on over. and we'll get out these little rectangle-y guys. Okay, once we do this, we will basically use Cauchy's theorem for a disk. That is, if we've chosen these guys small enough, we can get them all inside of a disk that lies in G. Why can we do this? Well, your book does it actually a slightly different way, but the easiest way is to use a lemma that we proved a little while ago, or talked about at least a little while ago, the path covering lemma from Chapter 1, Section 4. This said that we can cover a path between 2 points with little circles in a nice way, and a finite number of them in particular. So what we'll do is we'll just go, hey, if we do this right, well, then we can cover these paths with nice circles. We can cover the circles. In fact, we'll make sure we can do them so that we cover these rectangles. And each one of these rectangles, by Cauchy's theorem on a disk, if each of these circles is fully contained within G over here, then by Cauchy's theorem on a disk, these are all closed curves. So when we integrate around them, we get 0, right? And the big trick is just the exact same kind of thing we were doing at the end of last class when we were saying, hey, if you go like one way along something and then back along the other way, it'll cancel out. We're just going to integrate across all of these little guys, right? And then we're going to sum it all up. And when we go one way, it'll cancel out the other way. We'll know that all of these things are 0. They'll all go away. And then we'll be left with just a piece. We'll just be able to go along one edge and the other edge. And since we'll get 0 because of all of these circles, right? Everything adds up to 0 anyway because of that. We'll have what we want. That is, we'll say, oh, by Cauchy's theorem on a disk, each one of these pieces, every little chunk gets mapped to 0, and then we'll do a summation and say, hey, going from here to here, going about this, all of these little chunks counterclockwise. You add them all up, it's the same as going from here and then going here, right? And then we'll say that they're same, and then hey, if it's 0, then you can subtract one to the other side, right? So going here and then going here is exactly the same as going around all of them. Add them all up, and because it's all 0 anyway, you get out 0, and so then that means that this plus this gives you 0 when you go along that, and so that means that if you go here, then it's the same thing as when you go here, right? So it's just that breaking apart two paths into a closed curve business. That's the trick. Just a nice, hey, we can get a finite number of circles covering things. We can keep it all in there. That's the real trick. You need to use uniform continuity. You should read the proof in your textbook. It is a good proof. It just is has enough finicky details that it's not really intuitive to go over in class. However, it is worth mentioning, and this is kind of a big red flag that we've sort of brushed under the rug, is that realistically we actually should be talking about homotopies that are smooth enough. That is, everything we know about contour integration is with respect to piecewise C1 curves, right? Piecewise continuously differentiable. And while in this deformation theorem, we're assuming that gamma naught and gamma 1 are piecewise C1. We don't know that every curve in between them on the homotopy is piecewise C1. That is, for some intermediate parameter S, like this one might be C1 and the bottom one might be C1, but maybe in the middle they stop being piecewise C1. And so we really need to restrict ourselves to homotopies that have piecewise C1 intermediate steps. So we call these smooth homotopies or something like that, or piecewise smooth homotopies. That's a technical distinction that is critically important when we're rigorously proving things, but is it's one of the reasons it adds additional confusion to that last proof and makes it something that probably is not well suited to spend a bunch of class time on. All the same, it's important, and in fact, you can get around this requirement. If anyone is interested in that, I can send you some material about how that is done. But it's not worth us spending too much class time on. And what this brings us to after you've got the deformation theorem, a very nice and kind of obvious point. Think about our. Actually, we'll even prove this. So this is a great little end to it because it's really clean. This is the homotopy form of Cauchy's theorem. So if f is an analytic on a region G, and gamma is a closed curve in G, which is homotopic to a point in G, then the contour integral about it is 0. Oh, kind of nice. And this is the easiest proof ever. It's 1 sentence, 2 sentences. So if the curve gamma is homotopic in G to a constant curve, then, well, this is just going to be, think of it like this. If the curve is constant, its length is 0. I'll write this slightly more involved. You know that if you have, f has to be bounded on a constant curve, right? Because it can't be, it can't be unbounded. It just takes on a value, right? So the constant curve here, we're calling it lambda. Lambda f. Notice this is going to be in modulus at least less than or equal to the length of lambda, which is 0, times the upper bound for f in modulus, which is in fact going to be f of, well, z naught, right? And that's equal to 0 times whatever f of z naught is. And that doesn't matter because it's just 0. Hey, right on. So because, in modulus you get 0, you immediately get that this thing is 0. And since they're homotopic, they're the same, right? Bada boom. Nice. So this is a pretty result, which notice doesn't end up messing up things like 1 over z, right? Because, well, that guy might be homotopic on, say, like a disk or something containing the origin, or everything except the origin. It's not homotopic at the origin. So if you have a closed curve in there, it can't be contracted down to a point because it gets stuck on that little missing origin. And so there we go, the homotopy form of Cauchy's theorem. And that brings us to the end of this section. A whole lot of cutting up things in rectangles into smaller chunks using Cauchy's theorem for a rectangle, or cutting up rectangles into small chunks, then mapping them through a function, surrounding them by disks, and using Cauchy's theorem for a disk. Either way, we get out everything we had before, but in slightly more rigor. And I think that's a pretty great place to stop for Friday. All right. Cool. Remember to send me your proofs if you want some extra credit. If you don't care, then don't. But yeah, have a great weekend. I'll see you next week.